Okay, greetings everyone. Welcome in to my channel. I'm Professor L, and this is another live stream for Math Help. So if you have a math problem you want to see me work out, you can post in the chat. And I have decided to go ahead and graph the other greatest integer function, which is the ceiling function. Which is going to take it's going to produce almost identical graph. I call it the cousin of the floor function. So this function is called the floor function, and I'll just go ahead and get right into this. My markers are going to get switched out, but this is called a floor function. Because it's taking the largest number, or it's taking it's taking and returning the smallest integer. So you're going down an integer. The ceiling function is there's a cap, so you're going to be looking at the smallest integer that's greater than or equal to, rather than the largest integer that's less than or equal to. So it's opposite, producing a similar graph. Noting the open circles and closed circles, because when we produce the ceiling function, these two values will be switched. So closed circle signifying we're including the value, and the open circle is signifying that we're not including that value. So yeah, just hanging out and discussing math and hoping that I catch some people that want to hang out and do math too. And I promise I'll be friendly. And I'm going to go ahead and make that title. We'll erase it, because it is technically the greatest integer function. However, it's the smallest. So maybe I would call it the least integer function. And I get really confused sometimes by this stuff, but so instead of the greatest, we'll say the smallest. Because it's the smallest integer that is greater than or equal to x. Okay. And it's not a function, it's just so we've got the ceiling function. So we're looking for the smallest integer that is greater than or equal to x. And thus we have the ceiling function, and it is very similar with a few minor differences. Okay, so what are we looking at here? So we have f of x equals, and signifying we've got a cap here. We've got the floor, like the floor function, except for notice the difference. This is the ceiling function. And the ceiling function is defined as, let's see, it's n such that n is it's an integer, so it's an element of z, and n is greater than or equal to x. Let's say all that. So it has the same domain and range as the floor function. So we've got the domain is all real numbers, and your range is all. So we'll just say we're going to use set notation for that because since we're using it's only the integers that we're going to list. So we'll just say y such that y is an element of the integers. We'll have that scripted Z, and that should be sufficient. We're going to say y equals f of x, and we can go ahead and sketch our Cartesian coordinate system. We're going to need a pretty lengthy table. Very similar process to yesterday. This is giving me a little bit more practice, and it's helping me stall a little bit because I want to get back to trigonometry. And I remember really enjoying solving verifying and proving those trig identities. Those were really fun for me, and I seem to be pretty good at it. And so I just want to see if I can. I'm going to try to work on some over the next couple of days and see if we can get back to graphing some more of these complex trig functions. And that's kind of the goal. Okay, we got a Cartesian coordinate system here, and we're going to go ahead and we're going to pick a lot of values for in our domain so that we get a good idea of what this graph is doing. And so like yesterday, we went out to 2, I think. So let's see, we'll go 1, 2, and we will go up to 3 maybe. Okay, we're not going to go up to 3. All right, first attempt failed. We'll say 1, 2. There we go. That way I have enough partitions because I'm going to need some fractions. I'm going to need some rational numbers in here. So we'll say 1 and 2, and then that doesn't look real even, so scoot that over just a little bit. All right, that looks better. And I'll come out here, do a -1 and -2. And that's going to give me plenty of room to do my partitions in between. So we'll have some fractions in here. We'll say 1/2, and we'll say this one is 3/2. And then we'll get 1/4 in here. And the way I think about this to write these in real quick is that's 2/4. That would be 3/4, 4/4, 5/4. So that's technically 6/4 reduced. Then that would be 7/4, 8/4. We'll do maybe 1 or 2 on the other side of 2. So 8/4, 9/4, and then one more would be 10/2, which is 5/2, right? Okay, and then we'll just repeat, we'll mirror those values here. And that's kind of how I figure those out pretty quick. All right, make that a little bit longer. And let's see here. We have -1/2, and I have to remember, move out of the way. -3/2, -1/4, -3/4, 4/4, 5/4, 6 fourths, 7 fourths, 8 fourths, 9 fourths, and negative 5 halves. Perfect. All right. We got 1, 2, negative 1, negative 2. Needs to be a little bit further up. So important. So important. Okay. And see if that looks pretty symmetrical. One more time. Okay. For good measure. 1, 2, negative 1, and negative 2. Perfect. All right. So now that I have everything set up, it's going to go pretty easy, because as soon as I figure out what, according to this definition, this rule, as soon as I figure out what this ceiling function is doing, I can quickly just get some ordered pairs on the graph and start plotting my points, that old traditional method of graphing. Take any function in the world, as long as you can build a table and evaluate that function, you can develop a range of values and see where that, what behavior, what that function looks like graphically. Okay. So we're going to start out here, and remember, when we're reading this graph, we're going from left to right. So we're going from negative infinity all the way to positive infinity here. So we're going to start with our outermost values from the left hand here. So we're going to start with negative 5 halves, and we'll list a few of these. Negative 9 fourths, negative 2, negative 7 fourths, negative 3 halves, negative 5 fourths, negative 1, negative 3 fourths, negative 1 half, negative 1 fourth, and 0. We're all the way to 0. Okay. And we'll need one more table, but we're not going to worry about that. We'll just do the left hand first. So x, comma y, and we'll start evaluating this function. So we're taking, we'll first couple, we'll kind of put in here. And so we've got f of negative 5 halves. And so we'll plug it into this ceiling function, negative 5 halves. And the ceiling function saying, okay, we're taking and we're looking for the integer that is greater than, it's the smallest integer. Here, let's go ahead and explain what n is. N is the smallest number, integer, sorry, not, it is a number, but it's specific. It's an integer, smallest integer that it's greater than or equal to 2x. Okay. N equals the smallest integer greater or equal to x. Okay, right here. And that's what that's saying. And so right here, I'm looking at this value and my number line, and what is the smallest integer that is greater than or equal to negative 5 halves. And we're looking, and we're going to say that's got to be negative 2. Okay, right here, negative 2. So that point is on the graph. And 9 fourths, the same thing. We'll do a couple. F of negative 9 fourths. We'll plug in -9/4 in to that function. And what is the what's the smallest integer greater than or equal to 9/4? That's also -2. And then we can kind of just go through here and plug all these values in and kind of like mentally do it. The smallest integer that's greater than or equal to -2 is -2. Smallest integer greater than or equal to -7/4. Now we're at -1. We'll say -1, -1, -1, -1 is on there. And then same thing with 3/4. Now, the the smallest integer that is greater than or equal to 3/4 is 0. It's the next one. So all the way here, all the way to 0. And then now we have the positive values. So we'll go ahead and sketch these, plot these points real quick. So we've got all the way to 2. We're on the graph. All the way to a big circle. And then at -7/4, we're going to jump up. So at 2, we're going to have an open circle. And we'll go all the way to -1, close the circle. All those values are on the graph. Add for -1. And then at -1, we're jumping up to 0. So we have an open circle all the way to 0, and then we've got a closed circle. Okay, good. And then we don't have more points on there. So we've got all these points. And so we'll have to do the positive ones now. So we're going to list all the positive ones: 1/4, 1/2, 3/4, and I'll have to try to move out of the way. 1, 5/4, 3/2, 7/4, 2, 9/4, and 5/2. And that should produce a symmetrical graph of this step function. So let's see, 1/4, f of 1/4. So this is going to equal -2. This equals -2. That's why I put them here. So being silly. So we've got 1/4 here, and we're looking for the smallest integer that is greater than or equal to x. So the smallest integer greater than 1/4 or equal to 1/4 is 1. So this one is going to be 1. So we'll put 1 here, and we're going to say all these values all the way to 1 are going to 1. But then when we get to 5/4 now, we're going to 2. So all of these values will go to 2 until we get to 2. And then at 2, 9/4 is going to go to 3. Because the smallest integer that's greater than or equal to 9/4 and 5/2 is actually 3. So we would need another value up here. And we didn't leave room for that. So we might be able to go ahead and sketch over here. 3 would be about right there, wouldn't it? Okay, we'll get them in there. All right. So let's go ahead and sketch these other points in here. So we've got 0, and then at 1, we're going to have a open circle. And then all of these values to 1, 1 is on the graph, 1, 1. So we've got, and I made that a little bit too big. 1 is here. Okay. And then, so we'll kind of hold them up a little bit. All right, and so, all right. And then at 5/4, we're going to 2 now. So we're going to have an open circle at 2, and we're going to have a closed circle at 2. Sorry, at 2, 2, rather. And we got a line because all of those values appear on the graph. And then at that point, we're going to have an open circle at 3, and then we've got a couple of values there. 9/2, 9/4, and 5/2. So we've got that. All right. Okay. Again, here's your domain and range. And yeah, the ceiling function and the step. So it's a step function. So we'll put that in there. It's a step. We'll just leave it. And it's called a step function, I guess, obviously, because it looks like a little staircase. On to infinity and beyond. All right, let's see. Well, only 24 minutes. Finished. I did that in record time. So it must have been because I graphed 2 graphs in a row. I'm probably going to go ahead and stop there. It's been a long day. And yeah, so happy Wednesday. And I hope that everyone is having a wonderful evening. And if you watched my video and you liked it, thank you so much for watching. I really appreciate it. And I will be back again tomorrow. Hopefully I will find something relevant and useful. And yeah, if you want to, you don't have anything better to do on a Thursday evening, you want to come hang out with me on YouTube, then you could come and put problems in the chat if you wanted. Or you could give me a problem and I could work it tomorrow. That would be awesome. But anyway, I'll just be happy with whatever I get, and I will manage my expectations. I hope that everyone has a wonderful rest of your evening, and I will be back again tomorrow, same time, same place. Bye for now.